Hello, welcome to another module in this massive open online course. So, let us continue our discussion on applications of various applications of linear algebra, and let us look at yet another interesting area where linear algebra has several implications, and that is in Fourier analysis of signals, systems and so on via what we know as the fast Fourier transform. Alright. So, let us talk about the application of linear algebra in the fast Fourier transform, that is the FFT and the inverse of the fast Fourier transform. So, this is one of the fundamental operations, or we could say one of the fundamental linear operations in system analysis and signal analysis. So, FFT stands for fast Fourier transform, that is your FFT, and IFFT, many of you might be familiar, that is the inverse of the FFT, that is the inverse fast Fourier transform. So, this is your IFFT, and these are essentially, basically if you look at it, these are nothing but fast algorithms. So, FFT is essentially, nothing but a fast algorithm for DFT, and IFFT is a fast algorithm for IDFT. And what are DFT? So, DFT equals again this is your discrete Fourier transform, and IDFT, naturally this is inverse DFT, and these actually, as you see, this is basically fundamentally related to the Fourier analysis of signals and systems, that is to convert this time domain representation in a certain domain time, or in fact if you look at images and video spatial domain, into the frequency domain and draw valuable insights such as what is the high frequency content of the signal, what is the low frequency content of the signal, and so on. So, FFT and IFFT are essentially, so your FFT and IFFT, and we look at applications of these. So, FFT and IFFT these are valuable tools in the analysis of signals and systems, that is signals and system analysis, and this is basically what is known as the Fourier analysis, that is Fourier or the harmonic analysis. This gives rise to the frequency domain representation of signals and systems. Frequency domain representation of signals and systems. Okay. Now, what is the FFT or the DFT? DFT, all right. So, the FFT or DFT, which is essentially the same thing as the DFT, discrete Fourier transform, this is defined for a sequence. So, FFT or DFT is defined for a sequence This is defined for a sequence all right, and we have an n point sequence, correct, and so this is a finite n point sequence. And the FFT is given, or the DFT is FFT is given as, that is, if you look at x of k, that is the kth FFT point, or the kth, you can say the kth frequency bin. This is given as summation n equal to 0 to n minus 1 xn e raised to minus j 2 pi k over n. All right. So, this is essentially the kth FFT point xk, and we have the FFT points x0, and this is defined for k equal to 0, 1 up to n minus 1. So, you have n points. So, for an n point sequence, capital N point sequence, you have capital N FFT bins and the corresponding capital N FFT values. All right. So, this is defined for, so it is a one to one transformation, as you are going to see. This is defined for 0 less than equal to k less than equal to n minus 1, and this is 0 less than equal to k less than equal to n minus 1, and therefore, you will have x of 0, x of 1, you will have another output n point sequence, but this is in the frequency domain, correct. This is in the frequency domain. This is in the frequency domain, and xk corresponds to, as I said, kth FFT point. This corresponds to the kth frequency bin with normalized frequency, that is k by n. This is the normalized frequency, right. So, the kth FFT bin. So, this is essentially the normalized frequency. You can think of frequency bins 0, 1, 2, 0, 1 over n, 2 over n, k over n, up to n minus 1 over n. So, these are, so you will essentially have n frequency bins, and this gives essentially the spectrum, right. So, if you look at this, so xk is nothing but the spectrum of the signal, the frequency spectrum, or simply called as the spectrum of the signal, and you will call, and this is used in all domains. For instance, you will see the notation spectral analysis. All right. So, this is the spectrum of signal, and if you be more particular, you will have magnitude xk. This is what is known as the magnitude spectrum, and typically what is plotted, in fact. This is what is known as the magnitude spectrum. Okay. And now, if you look at the IFFT or the IDFT, right. So, the IFFT or IDFT, this can be defined as the IFFT or IDFT, which is the same as the IDFT. This can be defined as, naturally this performs the inverse operation. So, this will give you xn in terms of the frequency bins or the Fourier value. So, this will be k equal to 0 to n minus 1, 1 over n xk e raised to j 2 pi k n over n, and once again this is defined for 0 less than or equal to n. Again this is easy to see because you will get back the n signal values, that is 0 less than or equal to n less than or equal to n minus 1, and this is essentially the time domain. Again this is the time domain signal, right, and therefore you will once again you will have the n points x0 x1 up to, so you will have the n point discrete and in fact finite signal, finite you will have the n point finite signal. Okay. So, that is essentially the summary. So, you have FFT, right, FFT takes the signal x0 small x0 small x1 small xn, FFT gives you the Fourier or the spectrum of that capital X0 capital X1 capital Xn minus 1, you take the IFFT that transforms back from the frequency, that gives you transforms from the frequency domain and gives you back the signal, the sequence in the time domain, that is a small x0 small x1 small xn small x of capital N minus 1. Okay. And now the linear algebra part, now FFT and IFFT can be represented the FFT operations and IFFT operations can be represented as matrices, or rather you can say matrix transformations or linear transformations, right. So, these are nothing but linear transformations. And what are these linear transformations? That is, if you look at the FFT, for instance, you have the FFT, you have the FFT, the output is the n dimensional vector capital X0 capital X1 I can represent it as a matrix, in fact n cross n matrix and these entries will be, first all rows will be 1, first column all entries are 1, and this can be W, W square, W4, W square, W4, W6 and so on, W n minus 1, and the last entry will be W n minus 1 times, or you can say W n minus 1 square, W raised to n minus 1 square, right. And this is essentially your for instance, the entry here will be W raised to the power of n minus 1 and so on, and you can fill the rest of the entries, and this is an n cross n matrix corresponding to the n dimensional FFT. So, this is the frequency domain vector, this is capital N cross 1, and this is the time domain vector, and this is the n cross n, this is what you call as the FFT matrix. This I can denote by FFT. where what is this quantity w? This quantity w is nothing but the root of nth root of unity. This is given as e raised to j 2 pi over n, sorry, e raised to minus j 2 pi over n, e raised to minus j 2 pi over n. This is the quantity w, and you can easily verify, and this verify you can see Ifft, this is the Ifft matrix, and you can easily verify this. If you take the Fourier transform expression for the Fourier transform that we just seen above, write it in the form of a matrix, that is, you have the n input values x small x 0, small x 1, small x n minus 1, n output values capital X 0, capital X 1, capital X n minus 1. If you look at this as an n to n point transform, write down the matrix, you can easily convince yourself that this will be given by this matrix F I F T. And the important thing you can see here, one of the important things you can see here is that this is a transpose symmetric matrix. That is, if you look at any two elements, that is there is a transpose, this matrix is transpose symmetric, that is F I F T of I j equal to F I F T of G I, right. So, this is the transpose symmetry matrix, not Hermitian symmetric, transpose symmetric. So, this matrix is, do not get confused, although it is a complex matrix, it exhibits only Hermitian transpose symmetrics. Okay. So, do not there is a tendency to get confused because it is a complex matrix, but it exhibits only transpose symmetry. So, let us look at a simple example to understand this. For instance, let us take the case of n equal to 2, ask ourselves what is F I F T, F I F T equal to what? Naturally, this will be an n cross n, this will be a 2 cross 2 matrix. The W equals e raised to minus j 2 pi over n equals e raised to minus j 2 pi over 2, which is e raised to minus j pi, which is minus 1, and F I F T, this is equal to this matrix, I am sorry, F F T, F F T. I am sorry, everywhere here this has to be F F T. This is F F T, right, and F F T equals 1 1 1 W, which you can see. This case it is very simple, this is 1 1 1 minus 1. Okay, so this is a 2 cross 2 matrix, this is the F T, which is a 2 cross 2 matrix. Let us look at this for n equal to 4, it becomes a little bit more complex. N equal to 4, W equals e raised to minus j 2 pi divided by 4, which is e raised to minus j pi divided by 2, which is minus j, and therefore F T, the Fourier transform matrix, this will be 1 1 1 1 1 1 1. This will be W, W square, W cube, W square, W 4, W 6, W raised to 3, W raised to 6, W raised to 9, n minus 1 square. And if you substitute this and you can simplify these various expressions, for instance, you can see W equals minus j, W square equals minus 1, W cube equals W square into W, which is minus 1 times minus j equals j, W4, this is a fourth root of unity, so W4 is naturally equal to 1, W6 equal to W4 into W square, which is equal to minus 1, W cube we have already seen, W9 equals W8 into W8 is 1, so W is basically minus J. You use all these things and you substitute this matrix, so you will get FFT, this is the 4 cross 4 matrix, this will be equal to 1 1 1 1 1 1 1, this will be W which is minus J, W square which is minus 1, W cube which is J, W square which is minus 1, W4 which is 1, W raised to 6 which is minus 1, this will be W raised to W3 which is J, this will be W6 which is minus 1, and finally our W9 which is minus J, and this is the Fourier matrix. This is the 4 cross 4 Fourier matrix. And you can clearly see it exhibits transpose symmetry, that is, if you look at FFT of let us see, FFT of 2 comma 4 equal to J, which is the same thing as FFT of 4 comma 2, okay, exhibits transpose symmetry. And it is not Hermitian symmetry, because if it was Hermitian symmetry, then FFT of 4 comma 2 would be equal to the conjugate of FFT of 2 comma 4, that it would be minus J, right. So, it is not Hermitian symmetry, but it is rather transpose symmetry, okay. So, this is something that is important to keep in mind, not to get confused, okay. Now, let us now come to the IFFT matrix, and IFFT matrix can be written similarly. You can see, let us now come to the IFFT matrix, and the IFFT matrix is given similarly. This is an n cross n matrix. If you look at this again, this is nothing but you will get back the time domain representation. What does the IFFT do? It gives back that time domain representation from the frequency domain quantity. So, this will be 1 1 1 1, once again 1 1 1, W raised to minus 1, W raised to minus 2, minus n minus 1, W raised to minus 2, W raised to minus n minus 1, W raised to minus n minus 1 square, and you will have here capital X0. So, from the frequency domain get back the time domain, okay. And therefore, you can see this is again, this is essentially your IFFT, this is the IFFT matrix. This is of size, this is the IFFT matrix of size n cross n, this is of n cross 1, this is of size n cross 1, capital N cross 1, this is your small x's. Remember, we are using the small x's to denote the time, the capital Xx to denote the frequency, right. So, this is the time domain, this is the frequency domain, Once again you have the and if you look at this here, all the only difference here is this is the FFT matrix. If you are shrewd, you will observe that this is the FFT matrix with W replaced by W inverse, right. And what is W? So, this is nothing but FIFFT equals FFT matrix with W replaced by W inverse, and which is nothing but also W conjugate. And of course, plus there is a scaling by 1 over n, not to forget that. Sorry, there is a scaling, not to forget, in front of this there is a little scaling factor 1 over n. So, replaced by W inverse or W conjugate and scaled by 1 over n. Okay. And therefore, now since it is replaced by W conjugate scaled over 1 over n, you can see it is essentially the conjugate of FFT matrix, and plus you will have, and in addition you will have the scaling factor of 1 over n. So, you can see FFT, FIFFT, you can see an important relation, FIFFT equals you can say FFT conjugate, or since it exploits the transpose symmetry, conjugate will be the same as Hermitian, right. So, because Hermitian is nothing but conjugate and transpose, and this is nothing but FFT, you can say Hermitian. Okay. Now, the other interesting property that you will see here is that the other interesting property is that you have FIFFT into FFT equal to identity, right, because if you take the FFT and then followed by the IFFT, you will get back to the original signal. But remember, FIFFT is nothing but the Hermitian of FFT, right, of course divided by 1 over n. So, this implies that 1 over n FFT Hermitian into FFT equals identity. So, you can say this roughly behaves like a unitary matrix, because unitary matrix is when you have a matrix U says that U Hermitian U Hermitian equal to identity, but here you do not have exactly U Hermitian, but you have 1 over n times U Hermitian. So, it roughly behaves like an unitary matrix. Okay. So, roughly behaves like unitary matrix. So, this roughly behaves like a unitary matrix, alright. So, that is an interesting property. Let us look at the IFFT matrix. So, n equal to 2, let us again write this FIFFT. Of course, we know W equals e raised to minus j 2 pi over n, which is equal to e raised to minus j 2 pi over 2, which is e raised to minus j pi, which is minus 1. So, FIFFT equal to 1 1 1 W minus 1 or W raised to minus 1 W inverse, which is nothing but again, and of course, there will be a factor of 1 over 2, not to forget that, and that is essentially 1 over 2 1 1 1 minus 1. And if you now look at FIFFT into FFFT, this is equal to half 1 1 1 minus 1 times FFT, which is again the same matrix 1 1 1 minus 1, which is equal to half. Now you can easily see 1 comma 1 entry will be 1 into 1 plus 1 into 1 2, 1 comma 2 entry is 1 into 1 1 into minus plus 1 into minus 1, that is 0, 2 comma 1 is 1 into 1 plus 1 minus 1 into 1, that is 0, and 2 comma 2 is once again 2, and this is nothing but essentially your 1 0 0 1, that is essentially the identity matrix. This is the identity matrix. Okay, 2 cross 2 identity matrix. Quickly look at n equal to 4. What happens to the IFFT matrix? N equal to 4. So, F IFFT becomes 1 over 4. This is 1 1 1 1 1 1 1, and everywhere I have W, I replace by W minus raised to minus 1. So, W minus 2, W minus 4, I am sorry, W minus 1, W minus 2. W minus 3. You can also obtain by, as I told you, taking the Hermitian of the FFT matrix and dividing it by n. So, this will be equal to 1 over 4 1 1 1 1 1 1 1. This will be j minus 1 minus j minus 1 1 minus 1 minus j minus 1 j, and you can once again, so this is the 4 cross 4 IFFT matrix. Check, this is given as FFT Hermitian divided by 1 by 4. So, this you can check, okay, check, and also check that FFT into IFFT equals IFFT into FFT equals identity. Again, you can check this, alright, check these two propositions, which should be fairly simple for you to check. So, these are the FFT matrices of size 2 cross 2 and IFFT matrices of size 2 cross 2 and 4 cross 4. Similarly, you can construct other both FFT as well as IFFT matrices, and it is very simple to see the k comma lth element in the FFT matrix is essentially W raised to the power k L, or you can say, if you are indexing starting from 1 comma 1, you can say W raised to k minus 1 L minus 1, and the k comma lth element in the IFFT matrix will be 1 over n, where n is the FFT or IFFT size, times W raised to minus k minus 1 into L minus 1. So, that is essentially the relation, and we have seen both these matrices exhibit transpose symmetry, and you can say the FFT and IFFT matrix are unitary, except you have this factor, this annoying little factor 1 over n sticking around. So, you have to take the Hermitian to get the inverse of the FFT matrix. You have to take the Hermitian and divide by 1 over n, and to take the inverse of the IFFT matrix, you have to take the Hermitian and multiply by n, okay, depending on which matrix you are looking at. Alright. And as I told you, Fourier analysis is fundamental to the analysis of linear systems and signals. I mean, these matrices have several interesting properties. and these matrices arise extremely frequently in the whole of system analysis, in the whole of signal analysis, wherever you have images, wherever you have image processing, wherever you have image, for instance compression, we do something called your DST, discrete cosine transform, which is roughly similar to this thing, not exactly this thing your FFT or FFT, but it is very similar to the concept of Fourier analysis. So, image processing, image compression, image denoising, and I mean everywhere you can think of image reconstruction, this arises. We are going to see a very interesting application of this in the context of OFDM, that is orthogonal frequency division multiplexing, that is how do you analyze the OFDM and formulate it in terms of a linear system and analyze it using FFT, IFFT matrices and describe what the properties are going to be, what the resulting system model is going to be. Alright, so that is something we are going to do in the next module. So, let us stop here, and I urge you to again go through this once again to understand the concept of Fourier analysis thoroughly. Thank you very much.